I think some of you are there, right? Yeah, I see 1, 2, 3. We'll wait for some more time. One, two, three, four, five. Okay, we have, I think, enough number of people. So we'll start. Good evening, guys. So today we'll be seeing about amines and biomolecules. Yesterday, you don't worry about the problem. There are a few reactions. There are 1 or 2 reactions where the reactions are not there in the syllabus. So you don't have to worry about it. Like the end goal of all these problem solving is just to make you more familiar with the reactions and say what are the reaction conditions, what are the assumptions, how do you do conversions, right? So all these are the whole motto of all these problem solving sessions. Okay, right. And one more thing, yesterday when we stopped due to my current electricity failure, actually 2 minutes after that I got back current. But I thought like, no, like calling you back is not a good idea. So anyways, and today's class, I think, hope you all know, it will be a 2-hour session, right? So the timing will be from 6, that is from now to till 8:10, right? So by 7 o'clock, I'll give you a break for 10 minutes, right? You don't have to log out, you don't have to do anything, just unmute yourself and then just leave the phone, whatever it is, you can just leave. I'll also unmute and I'll stop the video. So after 10 minutes, we'll meet again. You don't have to go out of the meeting. Okay, is that clear? Right? And after that, 7:10, we'll meet again. 7:10 to 8:10. Right? So 6 to 7, 7 to 7:10 break, and then 7:10 to 8:10 will be the another class. Right? I hope this makes sense. Right? Cool. Fine. So we'll start with amines chapter. Right? You don't have much reactions as you saw in the previous chapter. There are very minimal number of reactions, but there are certain very important reactions. Right? Okay. And biomolecules, I don't think we have to look at anything, right? Please understand that biomolecules, you just have to know the structure, right? You have to know what is the straight chain structure we write CHO, CHOH, HOH, OH, HOH. So you have to know the structures of glucose and fructose, right? And you need to know what is the cyclic structure, right? You know there is the same what is that? The same straight chain structure can be converted into a cyclic structure, right? It's called alpha what is it, pyranosyl, okay, something, right? You have to know the names, right? And if you know, you need to know what are anomers, what are epimers, right? And you have to know why are we going for the cyclic structures, right? Can someone tell me why is it that we are going for cyclic structures? Why are we not all the properties regarding your biomolecules, especially your glucose and fructose, cannot be explained with the straight chain structure, right? So can you tell me what are all the properties that are not explained? Why are we going for the cyclic structure of glucose and fructose? There are few points, right?
Not proved, sir, in the straight chain structure.
It's not proved. It is proved. When I look at the spectrometry, right? When I look at there are some devices which can tell me the structure of the molecule. In some way, I'll be able to see the straight chain structure. But anyways, that is not the thing. Why, like, that structure is correct? Why is it that we are going for cyclic structure? Why? What is it mean? What is not being explained? There are certain things which are not being explained, isn't it? Right. So one of the things is your Schiff's base. When you go for 2,4 DNP test, right? When you go for 2,4 DNP test, basically your glucose and fructose has the aldehyde and ketone. So they should give positive test for 2,4 DNP, right? But what I see in reality is they are not giving. That means what? That means the aldehyde or the ketone group is not free, right? So it is in some other form. Basically, the some other form is what is your cyclic structure, right? Okay. So and then when you go for proteins, right? So when you go for proteins, you okay. Before that, so in sugars itself, I have something called as monosaccharides, disaccharides, and polysaccharides, right? So when you go for disaccharides, there is something called as okay. I have two monosaccharides. Two monosaccharide units are connected with the help of dash bond. What is the bond name? Or dash linkage?
Glycosidic linkage.
Absolutely right. You have to understand that it is going to be a glycosidic linkage. You have to understand how the glycosidic linkage. It's all about the structure. Nobody is going to ask you anything else, right? You just have to know structures. For galactose, I don't know what and all is there in your syllabus. You have galactose. You should have sucrose, obviously, right? Sucrose will be there. Galactose, maltose, lactose. I don't know, whatever is there in your textbook, that is more than sufficient. Like they're not going to ask more than that, right? Okay. And then when you go for your polysaccharides, I think you have only one thing, that is your starch, right? Again, you have to understand what are the I don't know how much is there in your syllabus, but you have different anomers of starch, right? I think it's alpha form, beta form, I'm not sure, right? There are different forms of starch, right? That you have to look into. Just know the structure. How is it? It's a polymer, basically, right? Again, it's only going to be glycosidic linkage, right? Okay, so that you have to study. So monosaccharides, disaccharides, polysaccharides, right? And then you have to know what are reducing sugars, what are non-reducing sugars, right? What do you mean by reducing sugars?
Reduce Felling's reagent.
So if they give positive test for Fellings and Tollens, not only Fellings, right? Fellings and Tollens, they're going to be called as reducing sugars. If they're not going to give me positive test, those are going to be called as non-reducing sugars. So basically all monosaccharides, your glucose and fructose, like that is what is there in your syllabus, they will be reducing sugars. But when I go for sucrose, right? Sucrose will be a non-reducing sugar, right? Okay. So that is that. Those are stuffs about what is that? Your sugars, carbohydrates, right? Okay. Next thing would be about proteins, right? Now you have to understand that protein is again a polymer, right? So it's a polymer of. What is a monomer?
Amino.
Yes, amino
Acids.
Yes, that's it, right? So it's amino acids. And amino acids, you have to understand that you should specifically tell it is alpha amino acids, right? What you have to understand is in the same carbon, you have the NH2 and COOH, and I can have so any other group, right? So this structure is common for any amino acid for that matter, right? Okay, so this structure is common, alpha amino acids. The same carbon atom will have an NH2 as well as a COOH, right? Okay. Again, you have different amino acids. You have essential amino acids, non-essential amino acids. Essential amino acids, we have to take it from the diet, right? Non-essential amino acids are already existing in our body, which are produced by our own body, right? And then you have to understand that basically these two, right? Two amino acids can be connected together with the help of what bond or what linkage?
Polypeptide.
Peptide linkage, right? So when I say a peptide linkage, peptide is basically an amide linkage. You can understand if I have CONH linkage, right, is what is my peptide linkage, right? So one amino acids COOH, the other amino acids NH2 will come together to form an amide linkage, right? So like this, if you have a polymer, this is maybe a dipeptide, right? Now you can have so many polypeptides. Polypeptides together, entirely together, are what are going to form proteins, right? So proteins are basically polypeptides, right? Okay, and what you have to know other than that, then you have to know about the primary structure, secondary structure, tertiary structure, and the quaternary structure of protein, right? So when I say primary structure talks about the straight chain. What is the sequence of amino acids? Say lysine, arginine, proline, serine, like that. You will have the sequence of amino acids, right? So that sequence, that peptide sequence, what are the amino acids consecutively present? That is what is called as your primary structure of proteins, right? Okay. Now, when I go for secondary structures, what is going to happen? I am going to have two primary structures. Say something like this. I'm going to have, say, I'm just writing very colloquially, right? So you're going to have two primary structures. Two primary structures will come together, not with the help of any proper chemical bond. It is going to be in terms of hydrogen bonds or disulfide linkages, right? You can either have hydrogen bonds or disulfide linkages, right? So two primary structures, two straight chains come together to form secondary structure. Okay, right? Again, if you go for now, when you have two secondary structures coming together, that will form a tertiary structure, right? And these tertiary structures will fold. I don't know whether you have seen any protein. You just check, right? You just check in Google the structure of proteins. You will see that it is like a ribbon going there and there. It is very complex structure, right? So that is what is called as your quaternary structure. So two primary structures to give secondary, two or more secondary will give tertiary, and tertiary will fold, right? The tertiary will fold to form your quaternary structure, right? I think in secondary or tertiary structure, I think you have in the tertiary structure only you have alpha helix and beta pleated sheets, right? So there are two types in which they can fold, right? One in the form of sheets or another in the form of an helix. Alpha sheets and beta, yeah, right? Helix and sheets, beta pleated sheets. Again, in beta pleated sheets, you can have parallel sheets or you can have anti-parallel sheets. You don't have to go into the details. Just know that these are all things which are there, right? No, you don't have to go into the details because this chapter is not that important with respect to your board exams. If you're going to get questions, you'll be maximum getting one or two questions, maximum. That's it, right? Definitely you'll get one question, maximum two questions. That's it, not more than that. Okay, and then that's about your proteins, right? Now, when you go for DNA, nucleic acids, right? So nucleic acid, you have to understand what are the components of a DNA, right? So you are going to have, I think biology students will be able to easily grasp it. I don't know how many of you are from biology here, right? So anyways, so when I go for DNA, right? So DNA has how many components? Say it has a sugar, that is depending on whether it's DNA or RNA, you're going to have deoxyribose or ribose sugar. That's actually carbohydrate, right? So one thing is sugar, a carbohydrate. Second, I'm going to have some bases, right? Bases, you're going to have the four bases you have: adenine, guanine, cytosine, and thymine, right? That is for DNA. And instead of thymine, if you put uracil, that becomes an RNA, right? Okay, so so you have this first one is sugar, second one is bases, the 4 bases, adenine, guanine, cytosine, and thymine, and instead of thymine, uracil and RNA, that you have to know. And third thing is your, or the third thing in DNA or RNA? What is the third thing? Sugars, bases, what is the third thing?
Phosphoric acid.
Not phosphoric acid, you should say it as phosphate. It's a salt of phosphoric acid. Okay, right? It's a salt of phosphoric acid. So these three things will be together, right? Okay, so now you need to understand two terms. So you have to understand these are all the components of DNA or RNA, right? And next thing what you have to understand is how they are linked together, right? So you have two things. One is what is called as your nucleoside, and the other one is what is called as nucleotide, right? Nucleotide is the entire molecule, right? Nucleotide is going to be the entire molecule. That is all these three things put together, right? Now nucleoside is only two. Which two are going to come in nucleoside? Can you tell me?
Base and
Nucleotide.
sugar.
Yes, absolutely right. You're going to have only the base and the sugar. The connection is what is called as your nucleotide. Sorry, nucleoside. Nucleotide is the overall thing. All three things put together. Okay, right? So and then you have to know DNA is hereditary material. I do my research on DNA and RNA proteins and stuff, right? So like if you ask me to talk, I can talk about another for 2-3 days among of all that. But again, you don't have to go into the details, right? So this much information, and you just go through your NCERT book thoroughly. That word by word, you go through. That's it. Done for the you are done for the chapter, right? You want like 2-3 marks, you're gonna get easily. You'll be able to score those 3 marks. Is it okay? Right? Any other doubts you have in this chapter? Biomolecules, anything specific you want to ask me? Okay.
No, sir.
Yes. Okay. Cool. Right. So if there's anything, you can always let me know. I don't know how many of you have my number. This is my number, and I hope you know my name. Guys, you can save it, right? So whenever you are trying to solve something, whenever you're trying to find the answer, if you're not able to get it, you're always welcome to WhatsApp me. Don't call me. Why does glucose does not give DNP test? Okay, right. Glucose doesn't give DNP test. If you look at the cyclic structure of glucose, you will see that there will not be any aldehyde or ketone. It will be in the hemiacetal form. You know what is the hemiacetal? The alcohol group will go and attack the CHO. So what happens there? You don't have any free aldehyde. So that is the reason why it is not able to give 2,4 DNP. Or in other words, I can tell that the percentage of free aldehyde is very, very, very less, right? And it is mostly found only in the cyclic structure. And that is the reason why it is not only glucose, even fructose is not going to give 2,4 DNP test. Okay. Right? I think the question is answered. Good. Fine. Okay. I just have to concentrate on just few more stuff in the previous chapter. I just want to ask you one question, and then we'll move on to the amines chapter, or your nitrogen containing compounds, however you want to call it. Right. Say I have carboxylic acid, benzene carboxylic acid, and you have I take an electron donating OMe, something I have, right? Now tell me, say I mark this as 1, this as 2, which is a stronger acid? Okay, let me give you one more stuff. Wait. I have COOH with an NO2, and this is 3. Okay, so tell me, can you arrange them in the order of acidic strength?
So the third one will be most acidic, sir.
Okay, fine.
And
Correct.
then first one and then second one.
Okay. Right. So what we expect, again, we are going to go for the stability of the conjugate base, as we already discussed so many times, right? You just have to remove all the H plus and check for the stability of this particular conjugate base, right? So we know what is the criteria for stability: lesser charge, more stability, correct? So if I can have an electron withdrawing group, that is going to bring in stability, because electron withdrawing means they will decrease the negative charge, correct? Right. So obviously NO2 I know is an electron withdrawing group, so obviously this comes first, no doubt about it, right? Okay, now when I compare these two, now I have OMe, which is an electron donating group, correct, which is an electron donating group. So I expect this to be less acidic than compared to this, right? But you know what I see in reality? I see that 3 obviously is more acidic, then comes 2, then comes 1. You know why this happens? I think you should have studied this. What is I'm looking for 2 words. What is the 2 words? Okay, I suppose nobody knows. It's called ortho effect, right? So what do you mean by ortho effect? Irrespective of whatever be the group, whether you put an electron donating group or you put an electron withdrawing group in the ortho position of this acid, it is always going to increase the acid strength. Please remember this. And what is the reason? Still we don't know. Research is still going on. There are various theories proposed, okay, but none of them is very conclusive, right? So in the exam, if they're going to ask this question, you are going to give this answer and tell them that this is more acidic than this one because of ortho effect, right? So what you have to remember, this is a very famous question. I have seen questions coming in board exams from this particular topic, right? So ortho effect means irrespective of whatever be the kind of group, whether it's electron withdrawing or electron donating, if you are going to put it at the ortho position, it will always increase the acidic strength of only carboxylic acid. This does not work for phenol. This does not work for any other stuff. This works only for benzene with a COOH. Only for that. Do not put like OH. You go for acid strength of phenol. At that time, this doesn't work. Whatever you have studied properly, that works, right? Only in this case of benzene carboxylic acids, ortho effect is existing. Okay, please make a note of it. Okay, cool. This is the only stuff I wanted to tell you, right? Ortho effect, very important, right? And just one more, if I have say propanoic acid, right? And I want to convert it into 2-chloro propanoic acid. One step. How will I do it? Single step. I have to do this conversion. How will I do it? So if I say single step, it's basically single reaction. That means I'm asking you something with respect to a particular reaction.
In the presence of red phosphorus and halogen.
What is the name of the reaction, ma'am?
Helmholtz-Zelsky reaction.
Yeah, absolutely, right? So basically what I'm trying to ask you is CH3, CH2, COOH. I want to convert it into CH3, CHCl, COOH. What I have to do is Cl2 in the presence of red phosphorus. If I do it, right, I'm going to get it. And the name of this reaction is HVZ reaction, or as she told, it's Helmholtz-Zelsky reaction. Okay, so this is also one of the name reaction, very important reaction. Okay, we didn't discuss this at all. That's why I gave you this stuff. Okay, guys. right? So we have completed everything. Like with respect to the first 3 chapters of organic, we are done, right? So we'll go to this amines chapter very enthusiastically, right? Is there any other doubt from this chapter, guys? From aldehydes, ketones, carboxylic acid, any other questions you have? Okay, as I take that as a no, you don't have any questions. Okay, fine. So what we'll do, we'll directly okay, we'll directly go for questions.
Sir? Sir, could you tell us about the nomenclature of amines for which the priority should be given?
Okay, cool. Primary amines are very easy, right? Primary amines are very easy. For example, say I have not benzene, right? If I have something like this, it's a primary amine. Primary amines are very easy. What you have to understand is the suffix is amine. Okay, right? So you just have to put cyclohexyl amine. Alkyl amine is what is the name, IUPAC name of any primary amine. It's very simple. Okay, now the problem comes when I go for secondary and tertiary amines, right? At that time you have to use N alkyl, something like that. Very simple, let me tell you that. Okay, for example, if you have CH3 NH CH3, oh, sorry, right? CH3 CH NH3 right? So what you understand is this particular thing, right? If this was a primary amine, if this was not there, what you would have done? This would have been methanamine, is it not? Methanamine. That is okay, right? Now, what you have in extra is CH3, right? And what I understand, this CH3 is not attached to any other carbon, it is attached to the nitrogen. So how will I write it? Is N-methyl methanamine. This is the IUPAC name. Again, you can ask me, sir, what should I do if I have 2 different alkyl groups? Let me take an example. Say I have CH3, CH2, NH, CH3. Okay, right? Fine. Now, what you have to understand is, people, the alkyl amine, methanamine, like that alkyl amine you write, that alkyl group should be a bigger group. That alkyl group should be a bigger group. So what I understand is this is the one which I have to take. Right? So this I write it as ethanamine, right? And what I have is CH3 extra. So you write N-methyl ethanamine. Okay, right? Now same thing will continue for your tertiary amines. At that time you have to go for N comma N. We'll see how to do it. It's very simple, right? Okay. Now say I take it in three different alkyl groups. Let me take say CH3 and C2H5. Say I have a cyclohexane, some 3 different groups I have, right? So again, what you have to do, you are going to write the alkyl amine with the biggest group, right? And the biggest group here is cyclohexane, right? So what should you end with? You should end with cyclohexanamine. I think last time I told something, cyclohexylamine, something I told. It should be cyclohexamine, cyclohexylamine. Okay, right. Now that is done. Now you have to account for 2 more alkyl groups, that is CH3 and C2H5, right? And you have to follow alphabetical order, right? Methyl, ethyl. Ethyl comes first, right? And you should not write normal ethyl. It should be N-ethyl, right? So how will I write? It should be N-ethyl, comma, N-methyl, cyclohexanone. That's it. Okay. Now, for if you have a double bond or triple bond somewhere, something like this, I don't know, like they will not complicate it much, so we will also not complicate it. Say I have NH2, something like this, right? Now, how will you name it? Again, this is normal primary amine. So 1, 2, 3 is pro. Now, you see here, cyclohexan, I forgot an A in here. Now, you see in all the examples, what you have done, we would have put an AN. AN corresponds to an alkane AN. That means there are no double or triple bonds in the molecule. That's what I understand, right? But if you find that there is a double bond or triple bond, instead of AN, you should use EN for a double bond. And if it is a triple bond, you should use YN, right? Now, whenever you're going, this is what is called as secondary suffix, right? Suffix is amine, right? Now, before that, you put another suffix called a secondary suffix, and that can only be three possibilities: AN, EN, or YN. Right? Now, in this case, I have to put EN, and you have to specify which number, which place the double bond is present. Okay. Now, please understand the numbering is very important. You have to understand that the carbon containing the amine is the one which is going to have maximum priority, right? So you have to put 1 here, not here. Please understand that, right? 1, 2, and 3. Right? Okay. Now you see in the second carbon atom, I have a double bond. Again, minimum number, right? You should not take 3. You should take 2 only, the smallest number possible, right? So prop 2 N EN dot N amine. That's it. Okay. So these are all the types of IUPAC naming. Did you understand, Kanna? Yes. Is it okay?
Yes, sir. So, don't we need to mention prop to in one amine?
You can specify, no problem at all. But even if you don't specify, in this particular case, it will work.
Yes,
because
sir.
you see in the first carbon atom only, whenever you have first carbon atom itself to have the functional group, you're going to have to specify. Say generally we don't write prop 1 ene, we write propene, because it's understood, right? Only the first carbon atom can have a double bond. It always works like that.
Yes, sir. Understood.
Right? Cool. So yeah, that's about IUPAC naming. Anything else you want to know, guys? A lot of questions will come from basic strength. Are you strong in that? Basic strength? Okay, fine. Then let me ask you a question. Fine. I have. Okay, fine. Like we'll talk about that later. Okay, so I have NH2. I have NH2 with OMe, or why am I putting always OMe? Let me put OH. NH2, CH3, NH2 with NO2. Say this is 1, 2, 3, and 4. Arrange them in the order of acidic strength. Okay, guys. First things first. What is the criteria for basic strength? Like we have acidic strength. What is the first? We'll go back to acid. What is the criteria for acidic strength?
Conjugate basis.
Conjugate basis.
Stability.
Right. So it's the stability of the conjugate base. Good. That is when it comes to acid. What is the criteria for basis? What is the criteria for basis?
The most stable conjugate base will be least basic.
No, Kanna. Here we cannot use, again, even if you're going to go for conjugates, here I should talk about conjugate acids, because these are bases, right? I have to talk about conjugate acids, but again, that is not the criteria here. Your thinking is good, but that is not the criteria here. There is some other thing. What is the thing?
Greater resonating structures, greater stability.
No. So if I ask you, I have CH3NH2 and aniline ARNH2, which, okay, we'll come back to this question later. You answer this question. Which is more acidic? Sorry, which is more basic? CH3NH2
CH3.
or
CH3NH2.
why?
Because of the presence of electron withdrawal of the aryl group, they are weaker bases.
Okay, I understand that aryl group is going to be an electron withdrawing group. Because of that, how is it related to the basic strength? Your answer is correct. Your explanation is little okay there and there, but you are not telling what is expected.
So due to resonance, the NH2 group is not ready to donate the electrons.
Okay, I'm nearing the answer somewhere. Okay, it is something related to the lone pair on electrons, right? Okay, so here comes, yes. Anybody wants to elaborate on this?
So in CH3NH2, because of the electron releasing nature of the CH3 group, the lone pair will be more available for protonation.
That's it. That's how you put it, right? So remember, guys, basic strength of amines is directly okay, maybe I'll write it somewhere where I have space. Okay, so here I'll write. So basic strength is directly proportional to the availability of lone pair on nitrogen. You're able to see? Yeah, you're able to see, right? So the basic strength is directly proportional to the availability of lone pair on nitrogen. This is the criteria, right? And remember, this is the criteria which you have to use if you find all the amines in gaseous phase. If you go for aqueous phase, again, something will be different. Okay, we'll go back to that later. Once we finish this, then we'll go back to that when what happens in aqueous phase. Okay, so and in the examination, right? If they don't mention anything about the phase, they didn't mention anything about the aqueous phase, or they didn't mention that it is going to be in gaseous phase. By default, it is gaseous phase, right? If they don't give you anything, assume that it is gaseous phase, and you answer those questions. Definitely, question will come from the acidic strength, basic strength. Definitely, questions will come. Okay, right? So at gaseous phase, the basic strength is directly proportional to the availability of lone pair. Now we can answering this question. Obviously, this is going to be a better base than this one. Obviously, because I know this is going to electron donating group. The availability of lone pair is more for protonation. Right now, if I go for aniline, you understand that the lone pair is not available on nitrogen. This is actually involving in resonance. Right? The lone pair is not available for protonation. Right? So the lone pair availability is less in aniline, and that's why it is less basic than the corresponding aliphatic amines. We'll come back to primary, secondary, and tertiary later, but I think we'll be able to predict it now easily. Right? So, anyways, now, okay, now this we understood. Basic strength is directly proportional to the availability of lone pair on nitrogen. Right? Now you can answer these questions now. 1, 2, 3, 4. Take a while, take a minute, and answer this question now.
So is it 4, 1, 2, 3?
Which is maximum, Kanna?
4.
4 is maximum. Okay. Right? No, 4 is not the correct answer. 4 is not maximum basic. Any other answers? So what I need to have for increasing the acidic strength, for increasing the basic strength, I should have what kind of group present? Electron donating or electron withdrawing?
Donating.
Absolutely, electron donating group. Right now, like I understand why you told this, because CH3 is going to be electron donating, right? But electron donating by what effect? CH3 is electron donating by 2 effects. What are those effects?
High effect.
Okay, induction effect, inductive effect, and then one more. Anybody else knows? One is inductive effect. Other effect by which it is electron donating in nature. And how do you explain that? Yes, someone is trying to tell something. Yes, come on.
Mesomeric effect.
No, it's not mesomeric effect. The effect is hyperconjugation. I think we already spoke about this, but I didn't explain you what is hyperconjugation. But again, we don't have to look into it, right? Fine. So what you have to understand is, because of hyperconjugation as well as your inductive effect, your CH3 is electron donating in nature. That's what you need to understand, right? Hyperconjugation is something like resonance, but not exactly. Generally, when resonance happens, it is always the pi electrons which will involve in the resonance, pi bonds, or say the lone pairs, or the negative charges, right? Those only will involve in the resonance, right? But in hyperconjugation, sigma bonds will involve in the resonance. You don't have to worry about it, right? You should have studied in your 11th class, but if you don't remember, nothing to worry about. Remember that CH3 is electron donating. Whenever you see benzene ring having a CH3, you should always talk about hyperconjugation only. Please remember this. Okay, whenever benzene ring is having CH3, you should always talk about hyperconjugation. Right, now I gave you a priority order: inductive effect, hyperconjugation, resonance. Which should be given the maximum priority? Inductive effect, hyperconjugation, resonance. Among these three, which should be given maximum priority?
Resonance.
Okay, then
Hyperconjugation.
and then
And
inductive. Understood, right? So always the first priority goes to first priority goes to resonance, and then comes hyperconjugation, and then comes inductive effect. Okay, for example, I find something is electron donating via hyperconjugation and something is electron donating via resonance, right? The one which is going to which was going to be electron donating via resonance will be a stronger electron donating group. Okay, I repeat my statement. I have two species. I can take the example from here itself. I have CH3, which is electron donating by hyperconjugation, but I know OH is electron donating via resonance, right? So if you ask me which is a better electron donating group, OH is a better electron donating group because it is electron donating via resonance, whereas CH3 is electron donating via hyperconjugation. Right? Okay. Now, so what should be the answer? What should be the maximum basic here? Obviously, the answer should be 2. Yes, right? Because it is electron donating by resonance. This is electron donating by hyperconjugation. So first priority goes to resonance. So this one is going to be maximum basic. Right? Again, why electron donating group? Because I have to increase the availability of lone pair on this nitrogen. Electron donating means it will increase the availability of lone pair. Right, so after 2 obviously comes 4, right? Because these both of them electron donating, this is more electron donating. That's it. Okay, after that, which should come? 1 or I think this is 3, right? I'm sorry. 1 should come, right? Why? Because here NO2 is an electron withdrawing group by resonance, isn't it? So when I compare the availability of lone pair on this nitrogen and this nitrogen, in this nitrogen is going to have lesser availability because NO2 is an electron withdrawing group. So then comes 1 and then comes, that's it. That is the order of basic strengths. Okay, right? Very simple. Whatever you did for acidic strengths, there the criteria was stability of the conjugate base. Right here, the only criteria is availability of lone pair. So exactly opposite effects will come. Whatever you did there and here, it will be exactly opposite. Right? So instead of this NH2, if I had put CH3, then 3 would have been maximum acidic. Then comes 1, exactly the ulta order would have come. Okay, so anyways, I hope everybody understood. Is there any doubt here from this question? Everybody understood why is this the order? Everything is okay?
yes, sir.
Okay, fine. I'm hearing only one noise, but I will take it as a representative noise. Everybody understood, right? Okay, cool. So now we'll look into what happens if I have primary, secondary, and tertiary amines in gaseous phase, in aqueous phase. They are not very, very important questions, right? Okay, so when I have, say, primary amine, let me look into gaseous phase first, then we'll go for the other one. All right, the gaseous phase is pretty simple. And the gaseous phase is pretty simple, right? Okay, so now you can easily tell, right, which is going to be maximum basic, primary, secondary, tertiary. Same concept, availability of lone pair. So primary, secondary, tertiary, which is maximum basic?
primary, sir.
Okay. CH3 is what kind of group? CH3 is electron donating group, right? Okay, let me compare one more thing also. I take ammonia also in the picture. Okay, right. Everything contains nitrogen, everything contains a lone pair, right? Okay, so CH3 we know is an electron donating group. So generally when I compare ammonia with a primary amine, where a hydrogen here is replaced by a methyl group, which is going to be an electron donating group. So what will happen to the availability of lone pair? In this case, will it increase or decrease because of the presence of CH3? Maybe I'll rephrase the question. What will happen if one of the hydrogen from here is replaced with NH3? What will happen to the availability of lone pair on this nitrogen? Will it increase or decrease? It's not that a tough question, right? Maybe put everything, like put it in a chat box. Everybody, please participate, right? So like arrange them, ammonia, primary, secondary, and tertiary. You put them in the order. Everybody, please participate. Put it in a chat box. You don't have to answer, unmute yourself and answer, but everybody participate. Put it in the chat box. Order of ammonia, primary, secondary, and tertiary amines with respect to their basic strength. Go for it. Okay, Aditya says ammonia, primary, secondary, and the least tertiary. Okay, then come on, everybody, do it. Niveda, please give the sign in greater than sign or less than sign, or else I'll not be able to understand. Okay, fine, Aditya. I understand what you're saying. Okay, cool. I don't know how many of you are there. 1, 2, 3, 4, 5, 6, 7, 8. 8 people are there. Please participate. Okay, fine. I got only 2 answers. One from Nivedita, the other from Aditya. I hope everybody is listening. Please go for it. Please answer it. Okay, Anirudh, I got an answer. Good. Okay, next. Come on, guys. Don't waste time. Quick. You may be correct or may not be correct. Doesn't matter. It's all about participating. Please participate. If my video would have stopped, I was looking at the chat. That's why. Okay. Fine. Okay. So I don't know what happened to others. I think they're not interested. Cool. So I'll give my order. The order is tertiary, greater than secondary, greater than primary, and the least basic is ammonia. Now it is pretty straightforward, isn't it? Right? Why? Now I know CH3 is electron donating group, just like how we saw in the previous question, right? Electron donating groups will increase the basic strength. Electron withdrawing group will decrease the basic strength. Right? Okay. So CH3 NH2 CH3 is there. It is going to increase the availability of lone pair. This side I have 2 electron donating groups. In this case, I have 3 electron donating groups, increasing the availability of lone pair on the nitrogen. Right? So obviously the tertiary will be most basic, then secondary, then primary, and then comes your ammonia, because ammonia doesn't have any electron donating groups. Right? I hope for everybody it is clear. Okay. Fine. Fine. Now this happens in gaseous phase. We have mentioned here, right? This happens in gaseous phase. Okay. Now when I go for aqueous phase, right? Now there are 2 criteria. One criteria is availability of lone pair. Obviously, there's no doubt about it. Right? One of the criteria is availability of lone pair. The other criteria is stability of the conjugate acid. Right? The second criteria when you go for aqueous phase is stability of the conjugate acid. We know what is a conjugate acid. Just like how you have conjugate base, after removing H plus, whatever is remaining is what is my conjugate base. Here, after adding H plus, whatever is there is what is called as my conjugate acid. For example, if I have ammonia reacting with H plus to form NH4 plus, now this is my conjugate acid and this is my base. After adding H plus, whatever is there is what is my conjugate acid, right? So if the conjugate acid is stabilized in some way, right, then I can say that this is stable. This is okay. This is a good base. Okay. Now, please understand the stability of conjugate acid. We are not going to use any effect. We are just going to use hydrogen bonding because we're talking about aqueous phase, right? The effect which you're going to use to decide the basic strength based on the stability of the conjugate acid is by using only hydrogen bonding. We are not going to use any effect. Okay, fine. We'll see what is going to happen, right? Cool. So I'll drop this part. Right now, this is already answered with respect to availability of lone pair. We know how the order is. This is the order, no doubt. Right now, when we see what happens when I have hydrogen bonding, I go for stability of the conjugate acid. Right. Okay. So let me write the conjugate acids of all the three primary, secondary, and tertiary amines. Okay. So I can write it like this: CH3 NH3 plus. Is it not? It should have been CH3 NH2. After adding H plus, it will become CH3 NH3 plus. Okay. Now this NH2 plus CH3 CH3 NH plus CH3 CH3. So these are all the conjugate bases. Sorry, conjugate acids of primary, secondary, and tertiary amines. Okay. Right. Now, please understand, people. Right. This is the charged species. Right. Now you understand that the NH bond in all these cases, this NH bond I have, right, will be able to form hydrogen bonds with water molecule. Right? How? Say this NH bond, I can have an oxygen, a water molecule like this. This is going to have del positive. This is going to have del negative. Again, I have a del negative here. So you see, this kind of hydrogen bonding is possible. Oxygen and hydrogen, or even you can even tell that nitrogen and this hydrogen can also have. Yes, definitely. Right. But this N with the hydrogen coming from water is going to be same for all these things. Why? Because all these things contain only one nitrogen. Is it not? So one nitrogen with one hydrogen coming from water is common for all these three. Right. But hydrogen with oxygen, that is hydrogen of the amine, right, and the oxygen of the water will form hydrogen bonds, and that is going to vary among these three. Why? Because this NH, number of NHs, number of hydrogens attached to the nitrogen is actually changing. Is it not? You see here, there are 3 NH bonds. Here I have 2 NH bonds, and here I have only 1 NH bond. Right? Okay. So please understand, more and more is the amount of hydrogen bonding, more and more this particular conjugate acids are going to get stabilized. Okay. More hydrogen bonding, more stabilization. And how will you account for more hydrogen bonding? More and more is the number of NH bonds. More and more is the number of hydrogen donors. We know what is hydrogen donor. Hydrogen attached to a highly electronegative element like nitrogen, oxygen, or fluorine. Right. Okay. So what I understand here, I have 3 NH bonds. Here I have 2. Here I have only 1. So which can have maximum extent of hydrogen bonding? Maximum extent of hydrogen bonding will be from primary because it has 3. And this next comes this, and the least amount of hydrogen bonding is possible from the conjugate acid of tertiary amine. Right? Now, obviously, with respect to hydrogen bonding, which is now maximum stable, obviously primary is the one which is going to be maximum stable because it can have more amount of hydrogen bonding, more extensive hydrogen bonding with water. And the least stable one is the tertiary, right? Because it is going to have only 1 NH bond, and that is going to have very less amount of hydrogen bonding with water, right? So if I keep this in mind, right, if I keep this in mind, this is with respect to the lone pair availability, right, this order. But if I look into the hydrogen bonding stability, right, can I say primary is more capable, I would say this exact opposite order is going to come. I leave ammonia, right? Okay, you can check this off. So now when I check it with respect to hydrogen bonding, stabilizing the conjugate acids, this is the order I expect. Primary, 3 NH bonds, secondary, 2 NH bonds, and tertiary is going to have only 1 NH bond, right? So as I told you, this is with respect to hydrogen, right? Okay, so now both these effects are very important, right? Availability of lone pair is also important. Only then the H plus can attack, right? And also after the H plus is attacked, the stability of the conjugate acid with respect to hydrogen bonding is also important when it comes to aqueous phase, right? So the overall effect, right, the overall order is going to depend on both of these, which is going to be dominant, which is going to be recessive, right? Say in some cases that the lone pair availability is going to dominate, or in some other case the hydrogen bonding stability is going to dominate, right? So you will see when I have when I have methyl groups, right? When I have methyl groups, secondary is going to have maximum basic methyl or ethyl, both one. Okay, we'll see how it happens when I have ethyl, right? So methyl group if we have R, basically this RNH2, RNH R dash, R and N, primary, secondary, and tertiary. When that R is methyl group CH3, right? You find that secondary is the one which is going to have maximum basic strength. Now it's pretty understandable because both with respect to lone pair availability as well as with respect to hydrogen bonding, you have secondary coming second, right? So both these effects are going to elevate secondary, right? Okay, then comes primary, and the least is tertiary for methyl groups. Now when I have ethyl, you're going to have secondary, tertiary, and then primary. Again, it's all about which is going to dominate. You remember this, okay? You remember that in case of methyl groups, hydrogen bonding dominates, because that's why you see primary is more basic than tertiary. Secondary, because both effects are good for secondary, right? Okay, now in this case what you have to understand, the lone pair availability dominates. That is why you see tertiary is more basic than primary. Okay, right? So again, as I told you, if they don't specify anything in the question, nothing about the phase, then they are mentioning only about the gaseous phase. You do not have to worry about any of this. But if they mention that it's an aqueous phase, this is how you solve the questions. Okay, I hope I made it clear. Any questions from this? Everybody understood? Yes? No? Okay.
Yes, sir.
Okay, good. Right, so this is about the basic strengths, and you will be able to answer any questions from basic strengths. Good, right? Okay, fine. So I'll run this part. Okay, now going for tests of primary, secondary, and tertiary amines, right? Now tell me, there are two tests. One test to confirm that is a primary amine, and second test is there to identify whether it's primary, secondary, or tertiary. Can you tell me both the tests? What would you do? What is the test which can confirm only primary amines?
Isocyanate test.
Or it is also called as
Carbylamine test.
Right, it's called carbylamine reaction or carbylamine test. You know what you have to do, right? So you have RNH2 with your CH. I think yesterday we solved a question based on this, right? CHCl3 bar KOH. You are going to get RNC. Okay, how will you you form the compound, but how will you prove that it is primary amine? With respect to what property will you be able to prove this?
Foul spelling substance will be formed.
That's it, right? This is going to have a very bad smell, right? Okay, so that is about test for primary amines. Okay, now how can you distinguish?
Doubt, sir.
Yeah.
Why does this carbylamine not happen for secondary or tertiary and only for primary?
Okay, what you understand is RNC is coming, and you see the C is coming from this one, CHCl3. That is how it is, right? So if it was secondary, right, if it was secondary, right, now where will the carbon come? If this carbon comes, how will you attach it is the question. You will not be able to attach it, right? Even if you're able to attach, you have something like this, Rn double bond C R dash, you have compounds like this, but that is not going to give me any smell like how this one gives, because isocyanide is the one which is having a bad smell. These are what are called as enamines, or actually in this specific case it's called imine. When you have N double bond C or C double bond N, it's called imine. Imines are not going to have any bad smell. Okay, so what you have to understand is you are inserting, you're basically giving a carbon atom to the nitrogen. That's what you're trying to do. If the nitrogen is in between two alkyl groups, you will not be able to insert that carbon atom into the nitrogen. And obviously, even if you insert, it is not going to form isocyanide. Isocyanide only will have bad smell. Is it okay? Is your question okay? Did I answer your question?
Yes, sir.
Okay, fine, good. Right. Like, I don't know whether you know this, Reimer-Tiemann reaction, this one, all these have similar mechanisms, right? What you would have known from your 11th class is you have three types of intermediates in organic chemistry, that is carbocations, carbanions, and free radicals. Okay, right? Free radicals we know, the chain initiation, termination, and propagation steps, all these things, right? So you have only three, like you would have studied only three, but other than that I have some other functional groups also. Those are what are called as carbenes, right? So carbenes are going to be something like this. It's like a diradical. Okay, CH2, the generally carbon will have 4 bonds, so 2 of the bonds are with hydrogen and 2 other electrons are just like that. They're not lone pair. No, please understand, they are not lone pairs. They are 2 individual unpaired electrons. Okay, so in this reaction as well as in your Reimer-Tiemann reaction, right, carbenes are the intermediates. Okay, just an extra information. If you're really interested about it, you can look into the net. Just see mechanism for your carbylamine reaction or mechanism for Reimer-Tiemann. You will find that these are the carbenes are the intermediates there. Okay, fine. So okay, good. So this I want to tell. Okay, that's about test only for primary. Okay, how will I distinguish primary, secondary, and tertiary people?
Heisenberg test.
Come again, what test? What test is it?
Heisenberg.
It's not Heisenberg, Anna, it's Hinsberg test, right? Heisenberg uncertainty principle is what we study in physics, like majority is physics, right? Okay, no problem. Right, so it's Hinsberg test, not Heisenberg test. Right? Okay, it's Hins. Okay, it's not test. Hinsberg test. Right. Okay, so in Hinsberg test, okay, what is this Hinsberg reagent?
Benzyl sulfonyl chloride.
Right, it's not benzyl, it's benzene sulfonyl chloride, right? So it is something like this, S double bond O and a Cl, right? Benzene sulfonyl chloride. Okay, C6H5 SO2 Cl. That's how you write it in short form, right? Okay, so we know how this thing works, right? So when I then, okay, along with Hinsberg reagent, what other thing which you have to use for Hinsberg test? Just this is enough for me to test. What other thing I have to use? What other thing I have to use? Okay, I'll run this.
Primary, I mean.
That is obvious, right? I have to use either primary, secondary, or tertiary. That we have to do by testing. In the reagent side, I have to use only this, or anything else is also required.
Alkyl halide, sir.
No. You use KOH or NaOH along with this. Is it not? Right. Okay. Anyways, we'll look at the reaction, then you'll understand. Okay. So if you have a primary amine RNH2, and if you have this one, I'll write it as NH2H for us to understand. Right. This is my Hinsberg reagent. So first step would be removal of this HCl. Okay. So what I have are NH, S double bond O, C6H5. This compound is going to get formed. Right. Now this compound, what will you understand is if I try to dissolve it in KOH, right? If I try to dissolve it in KOH, now see this hydrogen can come out as H plus. It is little acidic. Right? It is little acidic. Okay, so what will happen if I have a primary amine and I react with Hinsberg reagent and I form the compound and I take the compound, if I try to dissolve it in KOH, it will dissolve. It is going to form a clear solution. Why? Because I have an acidic hydrogen. This is a base. I have an acidic hydrogen, so they will react so that this one dissolves in KOH. That is for primary amines. Right. Okay. Now, if I had a secondary amine, RNH R dash, now let me write it like this. Right. Now again, I have my Hinsberg reagent C6H5. Now again, you will see that the HCl is removed. Right. If you have taken this down, can I rub this part? Only the first one. Okay. Now what will you have? This is going to form RN R dash S double bond O C6H5. Right. Now when I try to dissolve it in KOH, now you see there is no hydrogen here. Right. So no acidity is there. So this will not dissolve. That means it is going to form a precipitate. Right. Here you form a clear solution. Right. But if you have a secondary amine reacting with Hinsberg reagent and trying to dissolve in KOH, it is not going to dissolve. It is going to form something like a precipitate. Okay, right. Now I know what is going to happen if I have a tertiary amine. What do you expect tertiary amine to happen? Tertiary amine with Hinsberg reagent, what will happen?
No reactions.
Absolutely right. So you see, I have with your Hinsberg reagent, right? There is no hydrogen at all. You saw what is the first step? First step is removal of HCl, right? So now here there's no hydrogen, so there is no reaction at all. So primary amines reacting with the Hinsberg reagent, dissolve it in KOH, clear solution. The secondary amine will react with the Hinsberg reagent and trying to dissolve with KOH, it will not dissolve. And third, and when you go for tertiary amines, it is not even going to react with Hinsberg reagent. Okay, so like this, we'll be able to distinguish between primary, secondary, and tertiary. Okay, that is about Hinsberg test. Okay, fine. Okay, that is about the test. Okay. Right, and the most important things about in this reaction point of view is about your diazotization. Okay, so diazonium salts, you know how to prepare, right? Okay, so remember, when I have an aliphatic amine, generally only primary amines can form diazonium salts. Two, aryl primary amines, only aniline kind of things will be able to form diazonium salts. Aliphatic primary amines, fine, we'll see what happens, right? Fine. So for producing N2 plus Cl minus, what do I have to put here?
NaNO2 and HCl.
Okay, fine. So I have to put NaNO2 plus HCl. Now they both will react together to form what?
Nitrous acid.
Okay, what is the formula? Nitrous acid formula? I'm able to see that you're unmuting, but whatever you're telling, I'm not able to hear. Okay, fine. So nitrous acid formula is HNO2, right? This is little unstable, right? So that is why we are preparing it in situ. We already spoke about it so many times, right? Whenever you have a reagent which you want to use in a reaction, but that reagent is unstable, right? So you always like, okay, what was the other case where we saw this in situ? Which reaction which we saw? Where did we come across this in situ? In which reaction? Which reaction? What is in situ? Okay, I'll tell you, right? For the people who already know what is in situ, right? What where did we use this in situ preparation? Because in some other reaction also something not the same HNO2, but something else we prepared in situ, and that was reacting. What was that? Which reaction is that? If I have to give you a clue, formaldehyde and acetaldehyde can be distinguished by this test. Formaldehyde and acetaldehyde can be distinguished by this test. So which test, which reaction? That is the answer to the question which I'm asking. So HCHO and CH3CHO. How will I be able to distinguish? What reaction?
Iodoform.
Absolutely. Right now, can you answer what am I producing in situ there? What are the reagents for iodoform? Obviously, I have to use your carbonyl compound. What is the reagent used?
I and NaOH.
I2 and NaOH. Be very careful. Iodine gas and NaOH. Okay, together they will prepare. They'll form what? NaOH plus I2 will form what? CHI3 will be the end product, right? That is how we confirm the test, right? Alpha methyl groups are there. NaOH plus I2 is going to form something that is again in situ. That is unstable. I told you. That is why we are preparing NaI or
Sodium hypoiodide.
okay, the name is correct. NaOI, yes, Anirudh, right? NaOI, and obviously that is called as sodium hypoiodide, NaOI, right? So that is prepared in situ again because it is unstable. Okay, someone asked me what do you mean by in situ? In situ is nothing, Kana. In situ means that, see, for example, I have to prepare I have to use HNO2 in this reaction to form this, but I will not be able to store HNO2 in a bottle or a beaker. How you store NaOH or HCl because it is unstable, right? So what I do is in the reaction mixture itself, like by adding these two, I produce this. This is what is called as in situ preparation. Wherever and whenever required, I produce in the reaction mixture and then use it. Automatically, it will go on attack. That is what is called as in situ preparation. INSITU. Okay, whomever, I don't remember who asked that question. I hope it's clear for you. What do you mean by in situ preparation? Okay, cool. So we understood that aliphatic amines. What is the time, guys? Oh my god. Oh, 7:15. Do you need a break? Or will we, do you want a break? We'll take a break for 10 minutes. Okay. One guy says no need. I don't know about others. And most probably, okay. Fine, we'll take a break. Right. So let me complete this part alone. I'll just complete the diazotization part only for the aliphatic amines. 5 more minutes and then we'll take a break. So 7:20 to 7:30, we'll take a break. Okay. Right. Cool. So fine. So we know that aliphatic amines cannot form aliphatic diazonium salts because aliphatic diazonium salts are unstable. Okay, dialiphatic diazonium salts are unstable. The moment, and you see, even if you're going for unlean with HNO2 forming arene diazonium salt, you would have seen that the reaction happens only between this temperature, 0 to 3 degrees Celsius. Why? Because again, above this temperature, arene diazonium salt is also unstable. Right? So these reactions are performed only, these reactions are performed at very low temperatures. Okay, right. So fine. As I told you, this is unstable, right? So what is going to happen the moment you are going to form this Rn2 plus? Obviously, the Cl minus is the counter anion. So don't worry about it. What are you going to do is the nitrogen gas will be evolved. Okay, if I have to show you the mechanism, it's pretty simple, right? So this nitrogen is going to have a positive charge. Okay, N triple bond N is there. Now you see this bond pair will go along with nitrogen. So what will happen? The positive charge is neutralized by the negative charge coming as in the form of electron. N2 gas is gone. What is remaining? Now this R has lost your electron, so you will form a carbocation, R plus. Okay, and obviously you see this reaction will happen in the aqueous medium. So after that, the H2O will be there, right? So that will attack to form alcohol as the product, right? So please understand, if I give RNH2 with NaNO2 plus HCl, you should not write this. You should directly write alcohol. Okay, so this is a very good method of converting your amines directly into alcohol. This will work only for aliphatic amines, straight chain compounds, not for arene diazonium salts. Arene diazonium salts is stable. Okay, right? So you see, this is the mechanism. After the moment you form Rn2 plus and Cl minus, nitrogen gas is gotten out, you form a carbocation, and obviously everything you happens only in aqueous medium. Water will be there that is going to attack the carbocation to form the alcohol. Okay, fine. Let me stop here, people. Right? What is exactly the time? Time is 7:18. We'll take it at 7:20. We'll meet again by 7:30 sharp. Okay, take a break, we'll meet again. So I'm gonna unmute myself, I'm gonna close my video. I'll be back exactly by 7:30. You also be back. Do not go out of the meeting, just be there. Whatever you're using, just if you're using a phone, just lock it and go. If you're using a laptop, just leave it as such, nothing will happen. Okay, fine, we'll meet after 11 we'll meet 7:30. Be back. Okay, hope all of you are back. Are you guys okay? Can we start? Chris, are you there?
Yes, sir.
Okay, fine. So I hope good, fine. So I hope all of you are back, right? Okay, fine. As we are discussing about diasterization, right? Okay. Okay, fine. They're asking, I have to convert, like we're not talking about diazotization, we'll speak about it. Arene diazonium salts, you know, arene diazonium salts, once you form, you'll be able to convert them into so many functional groups, isn't it? Say you'll be able to convert diazonium salt into benzene. What is the reagent you use? Like if I have,
Ethanol.
okay, so you have N2 plus Cl minus 2 your benzene, right? So you can use MEOH, or Me means CH3, right? Or what is the other one,
H3PO2.
right? H3PO2. Okay, phosphorus acid, you can use, right? So like this, now you have so many name reactions coming here. You have Gatterman reaction, you have Sandmeyer's, right? These two are very important, right? So what happens in Gatterman? So basically this getting converted to your chlorobenzene or iodobenzene, or iodobenzene will not work, chlorobenzene or bromobenzene. What is the reagent for Gatterman? For Gatterman, what is the reagent which you have to use?
Copper powder.
Copper powder with? You have to use copper. Okay, then?
Halogen acid.
CuCl2, sir.
No. When you use HX, again, X can be either Cl or Br, right? So Cu in the presence of HX can be either HCl or HBr. You will be ending up with chlorobenzene or bromobenzene, and that is Gatterman. So same thing we'll use in Sandmeyer's, but only difference is this: what you're going to use. What is the difference between Gatterman and Sandmeyer's? What you're going to use here as a reagent? What is the reagent you have to use? Instead of copper bar HCl or copper bar HBr, what you have to use here in Sandmeyer's? Okay, so you have to use CUX bar HX, say CUBr bar HBr, or CUCl bar HCl. That's what you need to use. Okay, that is but the product is same, right? Only the reagents are different. In Gatterman, it is Cu bar HX. Here it is CUX bar HX. Okay, that is about this thing. Okay, fine. So how do you convert this to fluorobenzene? What do you have to use?
HbF4, sir.
Yes, right. I can use HbF4, and this is not mentioned, and I have to heat it, right? And this is also a name reaction, but I don't know whether the NCRT they have mentioned this is a name reaction. Do they know? Do you know what is the name of the reaction? Arene diazonium salt to fluorobenzene with the help of HbF4 and heating. What is the name of the reaction? Do you know? Is it given in NCRT?
No, sir.
Okay, fine. You can just know it's called Bals-Schiemann reaction, right? Bals-Schiemann. Okay, Bals-Schiemann reaction. Okay, fine. If I have to convert it into iodobenzene, what I have to use here?
NaI, sir.
Yes, right. You have to use NaI. Okay. If you want, you don't. I don't think so. You'll be able to convert it into phenol. No.
So if
Yeah.
you add water, it will come not the phenol.
Absolutely. I was about to say that. Absolutely. Absolutely. Right. So if you add water to this, you will end up with phenol. Right. So like this, you will be able to do so many conversions from the arene diazonium salt to different functional groups. Okay, fine. So now maybe we'll solve some questions. Okay. And obviously with diazonium salts, other than the conversions, there's one more reaction possible. What is the reaction called as?
Coupling reactions.
Yes, right. It's called coupling reaction. So if you want to know what is a coupling reaction, I have okay, I have N2 plus Cl minus. Now you have to take either OH or NH2 or CH3, either of this. Okay, phenol or aniline or toluene, anything you can use. Okay, now what you have to understand is you are going to remove the para hydrogen. This is a group and this is the para hydrogen, and you have to remove it. Okay, so how will you write the structure now? Structure will be N double bond N with OH or whatever group, OH or NH2 or CH3. This is your azo coupling reaction. Right, and you know these are colored dyes, and this specifically will be orange in color. Right, so these are used in textile industries for producing different colored dyes, azo dyes I call it. Okay, right. So anyways, so these are all the different reactions possible with diazonium salts, especially arene diazonium salts. Okay, fine, good. Now I think it's time for us to go to the questions. Okay, fine. So they're asking to convert ethanamine to ethanoic acid. Can you convert this? Two steps, you can convert it.
So convert it to phenol and then to acid.
Phenol or alcohol? How phenol is
Alcohol,
there a
I mean, sorry, alcohol.
Right, yeah, correct. So alcohol, how do you convert it to alcohol?
Nitrous acid.
Good, right? So you have CH3, CH2, NH2, you go for HNO2, or you write Na2 plus HCl, whatever it is. Now you will form CH3, CH2OH. Now you can go for any oxidizing agent, you will form CH3COH. Two steps, very simple. Right, okay. Say next question is okay, so you have chlorobenzene and they're asking you to convert it into para-chloroaniline. You know what is para-chloroaniline? Chlorine with, in the para position you are going to have an NH2, or say NH2 in the para position you are going to have Cl. Okay, how will you do this conversion?
First, we have you have to do nitrosation, sir. You have to get the NO2
Hydration.
group.
Yes, okay, then.
And then we have to add SN or HCl, that metal
Reduction.
with acid, so we'll get.
That's it. It's normal reduction. That's it. Reduction of nitro group to NH2. So very simple. Now this you go for nitration, HNO3 bar H2SO4. So now you know chlorine is ortho para directing only, right? So now you will have Cl with NO2, and then you go for SN bar HCl reduction to form this compound. Again, an easy conversion, right? Okay. Okay. Any other thing? Okay. So if I ask you, C6H5CH2NH2 and you have C6H5NH2, how will you distinguish this? Which chemical test can be used? Which chemical test you'll use? The clue is we saw that 3 minutes ago.
Nitrous acid.
Yes. If you use nitrous acid, what will happen then?
First, in the first thing we'll get benzyl alcohol, but in second one we'll get diazonium salt.
Okay, but still both of them will be colorless solutions. How will you identify? They don't have
With
any
primary amine, nitrogen gas will be liberated.
Okay, fine. Nitrogen gas can be deducted because nitrogen is little it's like a not supporter of combustion, so it will maybe say quench a matchstick if I bring a matchstick, but again not a good way of doing it. A better way, one is going to from diazonium salt, the other is not going from diazonium salt. So what can you do with the diazonium salt? Is there any way to make it colored?
Azodite.
That's it, right? You go for coupling reaction, right? So both of them you add NaNO2 plus HCl and then you add a phenol or something, you will see that the colored solution is going to get formed. So basically this will form the colored solution and this will not form the colored solution. Okay, right? Fine. So azodite test is what is your answer to this question, right? You have to form the diazonium salt, then you go for azo coupling. This will not form azo coupling, this will form azo. Okay, right, good one, right? Next. Right. Okay, now tell me, aniline is what kind of group? Ortho para directing group or meta directing?
Ortho-para.
Absolutely right. It is strongly activating group, right? So that's why you don't have to go for Friedel-Crafts reaction. You just have to put bromine in the presence of water. You will see that NH2 will have all the 3 ortho and para positions will be occupied by Br because it is very, 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 very strongly activating group, right? So generally what we go for bromination, we go for Br2 in the presence of AlCl3 or Fe or something. We go for Friedel-Crafts, right? But in this case, you see, I'm just using bromine water. All the 3 ortho and para positions are getting occupied, right? So how do I restrict this reaction? I want Br only in ortho or para position. What can I do to this? Right, I want
Acetic anhydride.
Okay, good. Right. So if I use acetic anhydride or any even when you go for acid chlorides, no issues. Right. So what is going to happen if I'm going to use that?
Acetylation process will take place.
Acetylation. Maybe I think you're trying to say you're trying to mean something else, but you're not putting the words properly. So what you have to understand is first, if I put CH3COCl here, what will happen? What will be the product?
NHCOCH3.
That's it. An amide is going to get formed. Is it not? I know amines with your what is that? With your acid derivatives is going to form amides. We already studied this, right? So what will happen? You will have NHCO CH3. Now you go for bromination. Say you put Br2 in the presence of Fe or AlCl3. You will see only ortho or para product. I don't want to write the other one. I don't want to write it. But how will you convert this into NH2 and Br? How will I convert this into NH2? What should I do?
SnHCl.
No. How do you convert an ester back to acid and alcohol? How do you do it? I have an ester. Okay. If I have an ester and I want to convert it back to acid and alcohol, what should I do? The same answer. Yeah, you can either go, basically you have to go for either base hydrolysis or acidic hydrolysis. You can directly put just H3O plus, right? So not only this, any acid derivative, we already spoke about this. Any acid derivative on hydrolysis will get back the acid and whatever the corresponding, whichever is left. Okay, now you can either go for H3O plus or you can go for NaOH, no problem at all. It is just what is catalyzing the mechanism. Either it's an acid catalyzing the mechanism or it is the base which is catalyzing the mechanism. So acid catalyzed hydrolysis or base catalyzed hydrolysis, you are going to get back the acid and the corresponding part. Okay, in this case, you will easily see that this is going to convert to this, and what will be formed is CH3COO Na if you use NaOH. Right, this one you have used CH3COCl, but what will you get is CH3COOH, and if you use Na, you're going to get CH3COONA as the byproduct. Okay, fine. So why are we doing all this? Is because NH2 is very, very, very strongly activating. So whatever type of reaction you do, you are going to get in all the three positions generally, especially if you go for bromination, right? So if you don't want that to happen, you convert amine into the amide by using an acylating agent. This is an acylating agent, right? So now the activity is little decreased, right? It is not going to be that strongly activating as in the case of NH2, right? Then you do whatever the reaction you want. You are going to get only ortho or para product. Then how do you get back the amine? Is just by hydrolysis. You are going to get back the NH2. Okay, right, cool. Now, right, same aniline, right? If I go for nitration, HNO3 and H2SO4, right? You are going to get NO2 here plus NO2 here plus NO2 here. Okay, so if I look at the percentages, right, I would say forget about these two. These two are what are expected, right? I know generally aniline is ortho-para directing, right? So these two are okay, but what I see is this is almost 43% in the reaction mixture. That is a very huge amount, isn't it? Right? 43% of the product is actually a meta product. How will you account for it? This is a very important question. A lot of times it is asked in board exams.
Because the ion
Anilium.
formed is meta-directing.
It is because
The anilinium ion formed, that's meta-directing.
okay. How do you form the anilinium ion?
I'm not sure about that, but I got this question in JE paper, sir, so I know.
Okay, so it's very simple, right? You're raising acids here. This acids will give me H plus, right? Now you see this will go attack the lone pair on nitrogen. Correct. So what will happen? Now this NH2, NH3 plus, now it doesn't have any more lone pair, right? So it is going to act as an electron withdrawing group, basically a deactivating group. And I know deactivating groups are going to be meta-directing. Okay, this is how you have to answer the question. Why is it that aniline on nitration gives considerable amount of meta product? is because the H plus coming from the nitrating mixture is going to form the aniline ion, which is metadirecting. Why it is metadirecting? Because you don't have any lone pair on nitrogen. It is not going to anyways be a what is that, electron donating group. It is now going to act as an electron withdrawing. That is why it is metadirecting. Okay, very important question, right? Okay, so this I wanted to tell. Okay, right. Okay, there is one more important reaction that we'll see in the form of a conversion. Okay, so I have ethanoic acid to methanamine. How will you do this conversion? Okay, if I ask you, for example, oh, fine, anyways, we'll see, we'll think about it. So you see, there's one carbon atom less. Yes, Hoffman bromamide reaction, right? So for Hoffman bromamide reaction, what is the reaction?
First, we have to convert the ethanoic acid to amide, sir.
Okay, good. Then you can go for Hoffman bromide elimination. Is it not? So if you remember the reaction, guys, RCONH2, right? Now, if what is the reagent which I have to use for
Br2 and KOH.
Absolutely, right? You have to use Br2 and KOH. You are going to form RNH2. Then what you see is there is one carbon atom less. This carbon atom is not there. Is it not? Right? Now, same thing only you will do. Right? So you have the ethanoic acid, CH3COOH. Now, how will you convert it into amide, CH3CONH2? What will you add here?
Ammonia.
Absolutely. Ammonia. Then you go for Br2 in the presence of KOH. You are going to form CH3NH2. Again, a very important reaction. It's a very useful reaction because you see there is one carbon atom less in the product. Right? Okay, good. Fine. What is the time? Okay, we have. I'll finish the class by 8:05, 8:10 guys. Okay, right? We'll just solve how many other questions possible now. Okay. Okay, I have to convert this to this. How will you do it?
First, convert it to diazonium and then to nitrogen.
Okay, diazonium salt, then convert to diazonium salt, then what will you do?
I can convert it to benzene and then convert it to nitrogen.
Absolutely. Right? Okay. Kana Anirudh, SN per concentrated HCl is for the ulta reaction. If you want to convert nitrobenzene to aniline, then you go for reduction. This to this, not this to this. Okay, so easier way is to convert it into HN. I use HNO2 to form N2 plus and Cl minus. Then you go for H3PO2. Then you go for benzene. Then you go for nitrogen. HNO3 bar H2SO4. You got it. Okay, good one, good one. Right, fine. Okay. Any other? Okay, now we'll do this problem. I have A with dilute HNO3 forms B, B with SN bar HCl forms C, C with NaNO2 plus HCl is giving, and you have to boil it, you get OH and OH. Okay, you have to identify A, B, and C.
Sir, B is nitrobenzene and C is aniline, sir.
B is nitrobenzene, C is aniline. Okay, but you're missing something else, I guess. So you have two OH groups here, not one. Okay, so I can say that A, or I would say if this I go back, right? So what you can understand is, people, this NaNO2 plus HCl bar heating, basically you understand that there is already H2O present. Is it not? Right? This is all aqueous medium. NaNO2 is a salt in aqueous, dissolved in water, HCl dissolved in water, everything is dissolved in water, and you heat it, you get phenol when you have a diazonium salt. That is, this is a two-step reaction basically. In this itself, I have two steps. One is the diazonium salt formation. The other one is to convert it into phenol by adding water. That is understood here. That is what you have to understand here. Okay. So what I understand is one of the OH is coming like this. The other OH should have been there in the initial molecule itself. That's what I understand. Right? Okay. So I can predict C like this. I had an NH2, definitely only then I can go for diazonium salt formation, and then I'll be able to convert it to phenol, right? So definitely there is one more OH already present. That's what you need to understand, right? Okay, now this is very easy. Now C is formed by reduction of B. So I can easily tell that B would have been NO2 with an OH, right? And you see, dilute HNO3 is added. Right. Now remember, for phenols and aniline, which are very strongly activating groups, okay, you don't have to go for nitrating mixture. Nitrating mixture is what? HNO3 plus H2SO4. Generally, when you want to go for nitrogen and a benzene ring derivative, you go for nitrating mixture to get NO2, right? But if I have OH, that is phenol, or aniline, you can just use dilute HNO3. It is enough for me to introduce NO2 into the benzene. Please remember this. Okay, you don't have to go for nitration. I mean, you don't have to go for nitrating mixture, right? So what I understand, this B NO2 is getting introduced with the help of HNO3. So A should have been what? A should have been A should have been what? If this NO2 is not there, basically this is getting introduced. If NO2 is not there, what is remaining?
Phenol.
Thank you so much. Right, phenol. Right, so this would have been phenol. So phenol with dilute HNO3 will give this, and then on reduction will give this, and then Na2 by HCl would have given me Na2 plus Cl minus, and still I'm heating with the help of H2O. You are going to end up with this. Okay, right? Fine. Okay. Okay, I want to give you a question. But what is the time? It's almost time. Maybe this is the last question for the day. So you have CH3COOH with NH3 by heating. You have A with NaOBr is forming B, and B with NaNO2 plus HCl is forming C. Identify ABC. Okay, A is amide, CH3CO NH3, NH2, not NH3. Right, this is an amide formation. A is very easy. So you'll form CH3CO NH2. Okay, what is this NOB? NaOBr. What are they trying to say here?
Haloform reaction.
Okay, that is what we think. But please understand, even if you put NaOH, or if I put KOH bar Br2, that is also going to form KOI. Or if you put NaOH bar Br2 or I2, whatever it is, this is KOBr. Right, here also you're going to form NaOBr. There are two ways of producing it. Sodium hypohalite, right? Sodium hypohalite can be produced with the help of your iodoform reaction, right? Or here, I think there also it's the same, right? There what we use in iodoform reaction? NaOH plus, yeah, NaOH bar I2. Here also it's the same, right? Here also it's the same, right? KOH bar Br2 or NaOH bar Br, the same thing, right? So you are going to form hypohalite. Like this is basically what reaction then? NaOBr. If I have an amide with an NaOBr, what is the reaction? Hofmann-Bromide reaction. Absolutely. Right? So this is Hofmann-Bromide reaction. You know what is going to happen. So B would have been CH3 NH2. You can see this carbon atom is less, right? Okay, what should have been C then? If I'm going for NaNO2 plus HCl, what should have been C? What should have been C? Aliphatic amines on diazotization will give what? Just we discussed, right? What happened there? Methanol. Absolutely true. So the answer here C is CH3OH. You can directly convert amine to alcohol if you put if you have an aliphatic amine to an aliphatic alcohol by with the help of HNO2 or say NaNO2 plus HCl. We discussed this, right? Okay. So I think we'll stop with this for today. CH3OH plus NaCl plus H2. Yeah, correct. Right? Okay. And we'll stop with this for today, right? I think tomorrow, what chapters we have? Tomorrow you don't have class, I think. Next class, what chapter do you have? I think it's definitely a physical chemistry chapter. I think it's solid state and solutions or something. I'm not sure. What is it? Can you check and tell me? Only solid state? I don't think so. Solid state and surface chemistry. Cool. Okay, fine. We'll do it. Okay, solid state, only few problems. It's only going to be problems and about the defects we'll study a little bit. And then surface chemistry is pure theory, right? So maybe I'll ask you some questions about surface chemistry and let me see how you are able to answer. Okay, fine guys. Thank you so much. You have been continuously 2 hours class. I know it's difficult, right? Thank you so much for your cooperation. We'll meet again, I think, on next Thursday. Until then, bye. Thank you so much.
Thank you.
Thank you, sir.
Yeah. Thank you.
Thank you.
Yes. Thank you. I'm going to end the meeting, guys. Thank you so much.